Okay, welcome to the second part of this chapter where we're discussing the Thevenin theorems as well as the Norton theorems. Again, we're talking about Thevenin theorems for AC circuits, and whenever we're talking about AC circuits, we're talking about complex numbers rather than the real numbers, as the case in the DC circuits, as we've seen in the Circuit 1 course. So what does the Thevenin theorem says? The Thevenin theorem says the following: any two terminal in linear AC circuits can be reduced to an equivalent circuit that consists of an AC voltage source in series with an equivalent impedance. So if you do have any circuit, you could replace this circuit with its equivalent. And what is this equivalent? It's two components. The first one is AC voltage source, second one is impedance, and both are connected in series. Now, this is the shape of the equivalent circuit. So if you have any complex network in this side, if you have very complex network at this side, component which consists of several different components, you could reduce the entire network into two elements, the V Thevenin and Z Thevenin. So equivalency means that when the same value of the load is connected in both original circuits and the equivalent circuits, the load, voltage, current are the same for both. So if you connect this R load, which is, let's say it is 100 ohm, if you connect it in the original circuit or in the equivalent circuit, the current which is produced in both circuits will be exactly the same. Now, this is when we talk about this impedance in Thevenin theorems. Now, how to find the Thevenin equivalent? So the first part is the voltage Thevenin. The voltage Thevenin is found using an open circuit voltage between the two specified terminals in the circuit. So if you do have this R load, just take it off and make it open and try to find out what is the V open circuit. We call it normally VOC, stands for open circuit. So you just remove this part and do measure what is the V open circuit, and it will be exactly the same as you can put it over here. Now, Thevenin theorems, we have to calculate also the equivalent impedance. So what is the equivalent impedance? You have to try to find out the impedance appearing between the two specified terminals in the given circuit, while all sources are replaced by their internal impedance, or in other words, are zeros. So you just replace it with zeros. So if it is a voltage source, you replace it with a short circuit. If it is a current source, you replace it with an open circuit. So try to measure out what is the Z equivalent from this terminals and do it the same, and keep in mind that you are zeroing all the independent sources. Now let's take an example. If somebody asks you to draw the Thevenin equivalent for the following circuits, which is in the page box over here, that is the circuit that you want to find out what is the equivalent circuit for Thevenin. In other words, you can replace you can look at the circuit from these between terminal A and B. So if you're talking about the first step, you have to remove the RL and determine the voltage from A to B. So simply just remove this RL and find out what is the voltage open circuit between A and B. If you try to find out what is the voltage between A and B in this case, it will be exactly the same as the voltage between these 2 points, which is the voltage across XL. So in this scenario, V Thevenin will be equal to VXL. So if you want to find out what is the voltage across XL, you will use simply the voltage divider rule, and then you will plug these numbers in, and you will find out what is the voltage across the VXL. So to find out what is the voltage divider over here, you put in the top the ZL and in the bottom the total and multiply by VS and plug these numbers and find it out. Okay, now the second step, you need to replace the voltage source with internal impedance, meaning the internal impedance for voltage source is 0, so you just change it with or replace it with a short circuit. So after replacing or zeroing all the sources, you need to find out what is the equivalent impedance looking between these two terminals, between A and B. If you look from this side, you will find out that the XL will be in parallel with R1. And if you try to calculate this quantity R1 in parallel with with ZL, you will find out that the value will be 44.6 and the angle will be 63.4. Finally, from step 1, to find out the final plot, you have to find out what is the V Thevenin, which is found in step 1, and Z Thevenin, which is found in step number 2. I just changed from the polar representation to rectangular representation because in this format I can separate between R and whether it is capacitance or impedance. In this case it is impedance. So I just plug these numbers in and find it out. This is the equivalent Thevenin circuits. Now, in summary, what are the steps to apply the Thevenin theorems? First one is to open the two terminals between which you want to find the Thevenin circuits. Normally it is RL. This is done by removing the component from which the circuit is to be viewed. Then you determine the voltage across the 2 points, which is the V Thevenin, and then determine the impedance viewed from the 2 open terminals with ideal voltage source replaced with short and ideal current source replaced with open, zeroing the sources. Third thing, just connect V Thevenin with Z Thevenin in series to produce a complete Thevenin equivalent circuit. Okay, so this is what is the Thevenin theorems in summary. Now let's see the other part, which is the Norton's theorems. It is exactly very similar to the Thevenin theorems, but rather than using voltage source as an equivalent, you will use a current source. And instead of using series connection, you would use parallel connections. So the Norton theorems is also an equivalent circuit that provides a way to reduce complicated AC circuits to a simpler form. The Norton theorems in fact says any two terminals linear AC circuits can be reduced to an equivalent circuit that consists of an AC current source in parallel with equivalent impedance. And this is the shape of the circuit. So we have the current source in parallel with impedance, and this is Norton source current and Norton impedance. Okay, for the Norton equivalent current IN, how to find this? We have to short the circuit current. So we have to find out what is the short circuit current. So if we find out what is the short circuit at the RL, so we are not replacing it by open circuit, we are replacing it by short circuit. That short circuit current will be equivalent to the Norton current. So just replace the RL with a short circuit in both circuits. So whatever current going through this short circuit, it is the IN in fact. So how to find the ZN now, the Norton equivalent impedance? So the total impedance appearing between the two specified terminals in given circuit with all sources replaced with the internal impedance, it will be equivalent to ZN. So first step, you have to open circuit the RL and then zeroing all the internal or all the sources inside the circuits. So if we do have a voltage source, replace it with short circuit. If we do have a current source, we replace it by open circuit. You can note that Zn will be always equivalent to Z Thevenin. So the Norton impedance will be equal to this Thevenin impedance. The main change between them is only the current source in Norton will be somehow connected to the voltage source in the Thevenin by the Ohm's law simply. So just if the equivalent impedance is the same, you just divide or multiply to move from one variable to another variable using Ohm's law. So in summary, the Norton theorem's steps are: first of all, replace the load connected to the two terminals between which Norton circuits with a short circuit. So in the Thevenin, we replace it with the open circuit. Here we replace it with short circuit. Second, determine the IN, which is the current through that short circuit. Third, replace take off that short circuit line and take off that resistance load. Then zeroing all the sources and replace them with their internal impedance. Then try to find out what is the total impedance between the two terminals, and that is the Norton impedance. The last step is you connect IN, the Norton current source, with the ZN, the Norton impedance, in parallel, and that will be constituting the equivalent Norton circuits. Yes, that's all. We've covered the Thevenin theorems as well as the Norton theorem for the circuits and what is the equivalent circuits in both of them, and how to calculate V Thevenin, R Thevenin, or sorry, Z Thevenin, as well as I Norton and Z Norton, and how to change between these two. Z Thevenin will be equivalent to Z Norton, and V Thevenin will be equal to I Norton times Z Thevenin or Z Norton, which is the same, and I Norton will be equivalent to V Thevenin divided by Z Thevenin or Zn, since it is exactly the same. Thank you for listening, and see you in the last part of this chapter.